Very welcome to Wireless Future, or rather welcome back after the summer break. This is episode 19. My name is Eric Larsson and I'm here as always with my colleague Emil Björnsson. Hello Emil, how are you today?
I'm great. It's good to be back after the summer break. I've used a lot of wireless services during my vacation.
Indeed, we all have, I think. So today we have the distinct pleasure of having as guest Thomas Marzetta. Tom is a distinguished industry professor at the NYU in Brooklyn, New York, and also the director of the NYU Wireless Center. He's a fellow of the IEEE and received numerous awards for his work in signal processing and communications. And perhaps he's most well known for his, seminal work on massive MIMO technology for wireless communications. He's also an author of the book Fundamentals of Massive MIMO, and I've had the privilege to work with Tom myself and learn from him, and also co-authoring the book, of course. So we are, again, extremely excited to have you here today on the show. Hello, Tom. How are you?
Very good, Eric. It's great to see you and Emil.
Very nice. I guess the way we're going to run this is that Emily and I will ask you and discuss with you various topics related to not only massive MIMO, but I think 6G in general, and also wireless research and where we see that heading for the future. So I think I'd like to kick this off by talking a little bit about massive MIMO specifically. Tom, you're really, I think, it's fair to say, the father of massive MIMO technology. And these ideas of using lots of small antennas that all cooperate phase coherently and build arrays of these antennas then to serve many users simultaneously that underpins massive MIMO is now more than a decade old. And I think it's also fair to state that when these ideas first were brought up, they were rather controversial, but they made it from being controversial and wild to becoming mainstream in research, to becoming mainstream in development, to becoming the cornerstone physical layer technology in 5G. And all this happened in something like less than 10 years. I mean, that's an amazing journey that I have been privileged to be part of and also fascinated by. So Tom, did massive MIMO evolve to be what you originally conceived? Or has it rather become something else? Or, when we see products today being marketed as massive MIMO, are these really massive MIMO the way you envisioned in your original inventions and papers more than 10 years back?
Well, certainly in terms of having large numbers of service antennas compared with active users, it's really happened, as you said. So, in fact, the start of massive MIMO, I believe, goes back almost 15 years now, and time really flies. But at the time, to talk about 20, 40 antennas seemed like a ridiculous concept, as you said, because base station antennas were sacred items. They were powered from the ground. You had these coax cables as thick as your wrist snaking up the tower. The idea of putting, even 20 antennas with their own RF amplifiers on the tower top was incredibly controversial. But the RF circuits, people really came through when they finally adopted the idea. All of the vendors sell 64-element active arrays, very compact things that you can lift, so that's amazing. It's happened.
Indeed, I think it is, and it's been a bit of a fun but also odd journey, I think, with the whole set of ideas underpinning massive MIMO, where folks at the very beginning were extremely reluctant to believe that it would even work, let alone be possible to implement using hardware and electronics that we could build in the next 10 years. Well, it all proved to be incorrect, in fact, and we have seen it happening faster than I could ever imagine. And now, again, I mean, it's the cornerstone physical layer technology that's out there in 5G and presumably for 6G as well.
Yeah, so, indeed. So when I started to think about learning what an antenna is, so I came in from the mathematical side, and for me, an antenna was everything that we are now calling an active antenna. It was the RF amplifier, there was the element that is radiating the signal and the processing and everything. So then it was easy when you were starting from the point that all these things will be integrated, that of course you can have an array of many of them. But then when you realize that, oh, this is not at all how we have been building the technology for tens of years, and that the technology need to keep up or be evolved before we can actually build something like this. So one thing that I know that you have said when it comes to massive MIMO and how we should design the systems is the quote, channel state information isn't everything, it's the only thing. So what do you mean with that?
Oh, well, of course, I borrowed that line from some famous American football coach. I don't know who it was, but who allegedly said, winning isn't everything, it's the only thing. And that was what he was famous for. But so what is it? Well, in order for the whole idea of massive MIMO is to have a fair excess of service antennas compared with active users. And when you do that, the service antennas at the base station can transmit at the same time and in the same time frequency resources different bit streams to different users. In order to do all this marvelously clever stuff, the base station antennas have to know the frequency response of every channel between themselves and all of the active users. That's channel state information. And if you can get that, then of course massive MIMO will work. It's the key thing. So how do you acquire this? This was one of the, you could call it the scientific discoveries, if you will, behind massive MIMO. One of them was quite simply, there were two such discoveries. One, and this was roughly about 2006. So one of these discoveries, if you will, was that you could add more and more antennas at the base station, and if you had channel state information, and things would get better and better. And the quality of the channel state information for each one of these channels didn't have to improve, which is a little non-obvious, because you might have thought that the more antennas I have, in order to make them work together, I need ever more precise channel state information. So this was not true. Great. The other was that to acquire this channel state information, the most efficient way was time division duplex, as opposed to frequency division duplex.
So, I mean, that brings us back a bit, I think, to this debate that never seems to end, right? With a frequency division versus time division, or FDD versus TDD duplexing, where, as many listeners will know, all the three of us here have been very early on adopting the view that TDD should be the way to go. Of course, that was highly controversial and still remains to some extent controversial, I believe, 10 years ago, right? So, and at some point, or to some extent, I could also recognize that there are legitimate reservations against going TDD. I mean, for one thing, you need to synchronize timing if you have different operators that share the same tower, right, in order to avoid the downlink of one operator to interfere with the uplink of another. And there's also this issue with coverage. If you have a peak power constraint rather than a long-term constraint on your emitted power, then essentially you lose 3 dB when you operate in TDD. And there might also be issues related to how long the guard intervals have to be in multicellular systems and so forth. But My view, I mean, notwithstanding those reservations, which I believe are legitimate, my view has been that FTD-based massive MIMO has never, isn't, and will never become as efficient as TDD massive MIMO. Is that also your view, Tom, or could you elaborate a little bit on that?
I agree completely with you, Eric. It's you brought up some issues which I typically don't bring up, TDD versus FTD, but ultimately no one has yet devised a way of acquiring channel state information as efficiently with FTD as with TDD. And while we're on the subject, in the United States, at least, and that's I'm not terribly familiar with the rest of the world in this regard. Of course, in the mid-band below 6 gigahertz, most of the, certainly below 3 gigahertz, most of the cellular bands are FDD, and they still are. And this should be changed. This is
it should be changed, but do you think it will be changed, or in what time frame will this be changed? I mean, it's always hard to make predictions about the future, obviously, right? But in a way, I mean, I would expect and hope and think that as the insight spreads more widely that TDD is fundamentally superior to FDD, then at some point operators and regulators would simply be forced to change. Will that happen, or where are we heading here, you think?
Well, of course, the operators are reluctant to change equipment. I mean, if a switch from FDD to TDD would make all cellular equipment and most handsets obsolete. And curiously, 5G seemed to have been developed almost with the idea of back compatibility as much as possible, in contrast with virtually all of the earlier generations of wireless. So I think that the fact that the United States still, and certainly below 3 gigahertz bands, is predominantly FDD, is more a reflection of business decisions than technical decisions.
Yeah, there definitely seems to be a lot of business decisions and also regulatory problems, that even if you would change all of the FDD bands to TDD when the current licenses are running out, there might be other services in the neighboring bands that will not wanting to change. Another issue that I have colleagues have been pointing out is also that the operators in TDD need to have the same uplink and downlink ratios, so that if you build your cellular network for downlink heavy traffic, which you probably will do if you're a cellular operator, then if you want to deploy another type of network for some, say, connected factory, where you have a lot of uplink traffic from video from robots or something, then it doesn't really fit into the template of having a lot of downlink traffic.
I've attempted on several occasions in the past to influence Federal Communications Commission to mandate this. The best response I've gotten from their chief scientist last year was that all new spectrum auctions specify TDD. So this is a partial victory, but really there's this incredibly valuable band with the spectrum, which is just going to be FDD for some time.
Yeah, it seems like we are at least heading in the right direction then. So one thing that have struck my mind is that if you read your book or also my book on Massive MIMO, both of us are sort of assuming that Massive MIMO means multi-user MIMO with one layer of data per user, and that we are sort of creating many layers by dividing between many users. So then I guess in reality we are you had the multiple layers, both over polarization and potentially over space domain as well. So why have you not studied that from the beginning of Massive MIMO?
So I assume by multiple layer, you mean sending more than one data stream to
exactly.
each user. Yes. Well, of course, the original attractiveness, if you remember, the original form of MIMO was point-to-point MIMO. The idea was you'd serve the different users in different time frequency tiles. Each user, however, would have a multiplicity, say 4 antennas in the handset. And you could, with, say a 8-element base station array, you could sometimes at least transmit 4 simultaneous data streams to each user. That was the idea. And one of the reasons this was, and just by way of this, a little bit of history, when I arrived in Bell Labs in 1995, my very first day of work, Jerry Foschini told me about point-to-point MIMO, and I got incredibly excited about the possibilities of that type of technology. But after a few years, it became apparent that the Lucent Technologies was not making any money off of MIMO, and what I was told was, okay, it requires very complicated, power-hungry handsets for one thing. Another thing is, unless you have a healthy signal-to-noise ratio, you don't get the full 4-fold multiplexing gains. You really get only 1 or 2 reliable data channels per user. And so this and other reasons was, of course, part of the motivation, much of the motivation for my looking at other approaches to MIMO. But let's just consider what's the biggest application of wireless going to be in the future. I mean, right now, people are very tired of the Zoom-like experience. And another point is, if you were to ask the person on the street or the person on the New York subways what 5G has brought by way of new services, they would look at you blankly, because no new services for the person on the street have emerged from 5G. It's you can talk about controlling drones, you can talk about telemedicine, you can talk about IoT, but autonomous vehicles, but there's been no new experiences for the typical user. Everybody who wants to stream video was able to do that under 4G, well, more than 5 years ago. And so we haven't had any new level in human-to-human communications for some time now. And so I've said for years, the next level of human-to-human communications will be augmented reality, virtual reality, everywhere, ubiquitous. And
that's exciting. I mean, with such entirely new applications that seem to be so data hungry that there's just no way that 4G or 5G, let alone 4G technology could offer them. Yeah, is that your vision for 6G, or what do you think will be really the driving applications for 6G, or are we done now? I mean, will there be a 6G, right? I think that's one question, but lots of folks are talking about 6G, I think, both in the academic world and also in industry. So could you elaborate a little bit on what do you think 6G will be? I mean, will it be these AR and VR applications for, say, human consumers, or will it be driven by something else?
Well, it depends on whom you talk to. Again, I certainly believe that we need something really exciting, or there isn't going to be a 6G, or it will be another evolutionary generation as 5G was. 5G, of course, as you mentioned, has some technological innovations. Massive MIMO for one thing, mobile millimeter wave for another. But we have to have some compelling thing that's going to hit everyday users, or it's not going to really be a new generation. They're not going to be willing to pay for cleaning out, replacing all of the current base station equipment and going out and buying entirely new handsets.
Right, like a new application also for everyday consumers. Yes, interesting.
But back, if I may, back to a question of a few minutes ago, why the emphasis on one stream of data per user? Why not more? Well, we're going to need that for augmented reality, because the sustained throughputs that people project for AR are staggering. 2-3 gigabits per second per user. So now let's consider, how can we get 2 gigabits per user? Okay. Well, suppose we have a 20 megahertz spectral bandwidth. Well, with a single channel, we would need 300 dB SNR at the receiver. And I haven't done the back of the envelope calculation, but I wouldn't be surprised if this is equivalent to the entire power of the sun of your base station. Okay, so forget about it. Supposing, again, 20 megahertz spectrum, supposing we stream 10 simultaneous data streams to the user, 30 dB, that's still a very high SNR. So if we streamed 100 parallel channels to each user, again, 20 megahertz spectral bandwidth, we could get it down to 0 dB finally. So, so let's suppose we go up to millimeter wave and give each user 200 megahertz spectrum. Well, again, a single channel is going to require 30 dB. That's a no-no, can't do that. Again, 200 megahertz of spectrum, 10 channels, yeah, we can get it down to 0 dB. So we're saying that if you can give each user 200 megahertz spectrum, you need to stream between 1 and 10 simultaneous data streams to do the job. And, you can go up, pretend we're doing terahertz, give everybody 2,000 megahertz of spectrum, 2 gigahertz. All right, one channel, 0 dB. So these are the types of numbers. So we're really being pushed in massive MIMO if we're thinking AR, VR to a stream or send multiple streams of data to each user.
Yeah. So I guess the 5G deployments that we have in Sweden are like 100 megahertz or so per operator right now in 3 gigahertz band, but that's still not enough if you want to reach several gigabits per second. And even if you have like 2 layers for polarization, it won't be enough. So when it comes to MIMO, then I suppose that, we have this 64 antenna products right now, and then a lot of our papers and other papers are sort of talking about the number of antennas going to infinity or being very large at least. So how do you see MIMO evolving now over this decade here? Will it become more antennas? Will it get another form factor? Or really, what are the main challenges that we need the technology to deal with?
Well, maybe it's best to just talk about what are people working on in terms of advanced versions of MIMO. Mm-hmm. So they go by different names, but let's just run quickly through them. One of them is cell-free massive MIMO. Another, extremely large aperture arrays. A third, intelligent reflecting surfaces. And a fourth, holographic MIMO. Mm. And so each of these has its proponents. In talking about these things, it's important to distinguish between what fundamentally does what you're doing bring new capabilities versus implementational considerations. Maybe this is a much cheaper solution and more economically scalable. So you have to keep these two factors separate in your mind.
Mm. So, I mean, you mentioned cell-free massive MIMO here, right? This one emerging technology, and in my view or my world, then there are a lot of say names and terminology that either mean or equivalent or nearly equivalent to self-read massive MIMO. For example, there's been talking for many years about network MIMO and distributed comp and comp joint transmission and so forth. In a way, to me, it is like self-read massive MIMO would be the ultimate form of network MIMO or distributed MIMO. But one could also argue that, I mean, comp joint transmission, for example, if we view that as some sort of implementation of self-read massive MIMO, it's already been tried and it never succeeded, right? So why did it happen? Why did comp joint transmission never succeed, but why will self-read massive MIMO meet with success?
That's a great question. So various people 15, 20 years ago had the idea of take a cellular network, or cellular MIMO, or not MIMO system, just a cellular wireless system. And instead of having each user served by a single base station, net the multiple, say the 6 surrounding or 7 surrounding base stations together and have them coherently transmit downlink, combine uplink signals coherently. And this went under various names, comps, network, MIMO, and so on. And it was evidently tried out to some extent and found both on pencil paper and I guess experimentally not to deliver any great big improvements. There are reasons for this. One is, if you think about it, you had a certain number of base station antennas, basically one sectorized antenna in each cell serving, suppose 10 users, okay? Well, suppose we did network MIMO. Well, now we would have 7 base station antennas serving 7 times 10 or 70 users. So the ratio of service antennas to users is the same as before, which of course, the whole idea of massive MIMO was to have a large excess of service antennas compared with each user. So this fundamentally is what doomed the network MIMO comps idea. The other difficulty with it was that, of course, under FDD and, of course, under the 2G, 3G protocols, it wasn't possible to get the channel state information at the base stations in order to do any meaningful, coordinated, coherent transmission.
So in a way, we're back to, I mean, where I think we started the conversation almost, right, with the fact that channel state information isn't everything. It's the only thing. I mean, it tends to be the accuracy of the channel state information that we have at the base station and at the transmitter when the base station transmitting downlink tends to be the ultimately limiting factor of performance in a multi-user MIMO system. And that combined with the fact that in order to make reasonably simple signal processing algorithms to work, then there has to be an excess ratio of service antennas to number of users. So these are really the two aspects in which comp joint transmission and earlier attempts to build anything like self-read massive MIMO or network MIMO, and that's really where these attempts failed. That's interesting, and I think also rather consistent with say my own understanding. I'm not sure, Emil, if you have any other or additional thoughts on that.
No, I definitely agree, but I think it could be of interest still to hear your motivate. Why do we need this excess number of antennas? I believe that one reason why people were not considering that in the 90s, where they started to talk about MIMO things, was that if you start to say, okay, how many streams are we going to transmit? Well, we will transmit the best you can get is the minimum of the number of transmit and receive antennas, or the minimum of the number of base station antennas and users. And then from that logic, there is no reason to have an excess number of antennas because we can't get more streams out of it. And then sort of people did at that time already look at like some asymptotics, letting the number of antennas and users go to infinity, but not with an excess ratio of antennas. So from that perspective, one of the real core novel things with the massive MIMO approach was this excess. So could you perhaps elaborate for the benefit of our listeners, why did you come up with this concept of having this excess?
Oh, wow. I guess because I'd exhausted every other possibility, it seems. But yes, I mean, I have to reach back 15 years. So what was I thinking of at the time that such that I considered? And I guess what we were honestly, I can't really recall what it was that clicked into place.
But I mean, isn't the main point here that you want this excess number of antennas relative to number of users in order for simple, which practically means linear, signal processing algorithms to be useful and even nearly optimal? I mean, if you have, 100 antennas and 10 users, then even the simplest possible linear precoder and decoder algorithm will be will perform nearly as well as the information theoretically optimal algorithm, which in itself can be highly complicated.
That's correct. And that, of course, is probably what I was thinking about. I remember during the summer of 2006, I realized that we could just add more and more antennas. And if we had CSI, a channel estimate with the same amount of noisiness, that didn't improve any, but we just added more and more of these antennas with noisy CSI. Things got better and better. And I remember showing this to my colleagues at Bell Labs, colleagues in the wireless business unit of Lucent, and everybody was surprised, even though this is a rather simple thing to show. And
indeed, I mean, I think we touched upon this point also earlier in the conversation here, right? That although when we add more and more antennas, we also increase the number of unknowns. I mean, for every new antenna you put in the system, there'll be an additional unknown channel impulse response to the terminals that has to be estimated. Notwithstanding that, performance still improves when we add antennas. I think at this point it might also be appropriate to point to the danger of speaking of adding more and more antennas, and particularly doing asymptotics in the number of antennas, which of course a number of early and influential papers have done, because I think to this day there is a remaining misconception that massive MIMO or even its rigorous performance analysis would rely on anything like assumptions that number of antennas grows to infinity and so forth. No, they don't, right? I mean, there is a rigorous theory for characterizing and optimizing massive MIMO performance that's useful and valid for any number of antennas. So this is something that I think Emily and I have worked hard on trying to convey to the community, that there's never any need really for anything like asymptotics or talking about infinity or anything like that. Well, yet we want a reasonably large ratio between number of service antennas and terminals in order for simple and linear signal processing algorithms to be useful. But there's nothing inherently anywhere in massive MIMO that entails the use of asymptotics or talking about the infinite number of antennas or anything like that. So yeah.
Mm-hmm. Yeah, so the way that I would perhaps explain the concept is that if you have an equal number of antennas and users, then if you tell the users to stand at precisely the right places, you could get nice orthogonal channel to them. You don't need any complicated processing or anything like that. But when you are then adding excess number of antennas, you get this possibility to let them be whatever they are, and you can still handle interference. So I have a thought. You talked earlier about having these new services like augmented reality or maybe virtual reality requiring very high data rates as something that is coming in the future. And then, we could stick with a few 10th or 100 megahertz of spectrum and try to create a lot of layers of or data streams to the users. But then you will need to have a lot of antennas in the device, which would maybe push you up to higher frequency bands. Or if you are anyway going up to higher frequency bands, you will probably find more spectrum. So from that perspective, do you see is it inevitable that we will gradually move to higher frequency band like millimeter wave or beyond, or is this just something that we are exploring now because we are lacking other things to explore?
Of course, yes, there are many people who believe the future is to push to ever higher frequencies, and I personally think that given that there's such a huge amount of spectrum out there, we've got to work very hard and try to learn how to exploit it. That said, though, I don't think it's a trivial task. So, for example, one of your podcasts or your Massive MIMO site, Eric, a couple of years ago, did a back of the envelope analysis, basically predicting that ultimate Massive MIMO spectral efficiency is inversely proportional to the carrier frequency. So this and it was based on the simple notion that going from 3 gigahertz to 300 gigahertz reduces the wavelength by a factor of 100, meaning the channel changes 100 times as fast. So if I had a millisecond to estimate the channel at 3 gigahertz due to high mobility of the terminals, I would have a microsecond to estimate the channel at 300 gigahertz. I'm sorry, it would be 10 microseconds, a factor of 100. 10 microseconds. And so, of course, there may be a countervailing effect that as carrier frequency goes up, the delay spread of the channel shortens, and so the frequency coherence increases. I don't know if this has been really demonstrated yet at all, but there are just, even if I didn't want to do MIMO or Massive MIMO, if I just wanted a simple point-to-point link in line of sight propagation conditions, as I shorten the wavelength, the problem is my receive antenna in the handset, in order to remain omnidirectional, gets smaller and smaller, scoops up less and less power. So I have to have a bigger array at the base station. And it's basically, you can show that if all of the growth in the array size or numerical size of the array takes place at the transmitter, the number of active antennas goes as the square of the carrier frequency, which means 10,000 times as many antennas at 300 gigahertz as at 3 gigahertz. Now, if you assume somehow that you can split up, make an antenna array numerically as big at the handset as at the base station, then it goes linearly, but that's obviously not a practical thing to do. And so this is what really terahertz advocates are going to have to face. There's also the fact that electronics, it becomes very difficult to create significant power at 300 gigahertz. I'm not saying these problems can't be solved, but they have to be solved.
They have to be solved. I mean, of course, the motivation for going to higher carrier frequencies is that there is more bandwidth available, right? And then the question is now, well, there's more bandwidth, no question, but will we be able to achieve the same spectral efficiency in these bands? And it seems that even leaving aside, I mean, the issues of mobility and channel training and so forth, just talking about like transmission or beamforming to a single terminal, that might be a challenge because of the link budget, where essentially, I mean, the path loss doesn't change, right? The path loss is substantially independent of the carrier frequency. What happens when you go up in frequency is that the effective area of an antenna, say a dipole for the sake of argument, shrinks proportional to the wavelength squared. So the effective area shrinks, which means that in order to maintain the same SNR or the same link budget, then either we need multiple small antennas that we control the phase, like a phased array or a MIMO array, or we need a physical antenna with a large aperture, which then is going to have a high directivity, and that antenna has to be pointed in the right direction mechanically. I mean, these are the two options that we have, right, in order to maintain the link budget. Either a massive MIMO array or something like a dish or horn antenna that we mechanically steer towards the location or direction where the terminal is located. And we haven't even talked about the blocking problems. I mean, but it seems to me to be a widely spread, unfortunately, myth that one can achieve the same spectral efficiency or the same link budget with a millimeter wave or even terahertz link as a link at the microwave band, whereas I argue that one can't, right? I mean, unless the transmitter is equipped with a large antenna array, either a massive MIMO array that has accurate channel state information, or a mechanically large array which inherently has high directivity and which has then to be mechanically steered and oriented in the right direction. You want to comment on that, Tom?
Yes, well, curiously, the mechanically steered dish, every time I suggest that to a millimeter wave or terahertz advocate, they just want to dismiss it. It's old-fashioned, mechanical stuff is unreliable and expensive. But in point of fact, during World War II, something called conical scanning was developed, which is an automatic way of maintaining a dish antenna pointed at a user. This was a marvelous idea. The idea is you, instead of pointing the antenna at a fixed direction, you sort of nutate it around. So it's actually pointing in a circle about a point. And you basically take horizontal and vertical spatial derivatives, which could be done with coherent detectors. And you have a servo mechanism that tries to drive these derivatives to zero. And when they're at zero, you're pointed right at the target. And
yeah, I mean, but Tom,
marvelous.
I mean, certainly this can be built, right? I mean, my point was not that we should build mechanically steered antennas. My point was rather that in order for millimeter wave to achieve the or to achieve the same spectral efficiency as the lower bands, and then we need to maintain the link budget. And there are really only two ways of doing that: either a high gain antenna that we steer mechanically, or a massive MIMO array with small electronically controlled patches or dipoles or whatever, right? I mean, there's just no way around that from the physics, I think. So
I think one thing to keep in mind here as well is that sometimes I get the feeling that people who advocate for millimeter wave bands are getting the feeling that we have never used antenna directivity in the past. So now when we go up in the frequency range, we will add it and that will save the day. But we have had base stations with high directive antennas since the beginning, like 15 dBi antennas or more. And then we, of course, need to maintain that high directivity. And if we then just need to have higher gain and still being more and more narrow, or have the flexibility in a MIMO array. And I guess from the user perspective, we have been having the luxury that we could have a approximately isotropic antenna in the handset, so we can turn it around in whatever way you like and it will work. But then when we go up in frequency, we'll need to have like a phased arrays that they have in the new iPhones in order to sweep around and try to maintain some reasonable gain when you are turning around.
But Emil, I mean, that's a good point indeed. I mean that even antennas in a conventional base station have a gain which is quite substantial, right? I think it's at 15 or something dB. But the point is, I mean, when you shrink the carrier wavelength and go up in frequency, then we need directivity, which not only has this 15 dB to start with, but a gain which is the 15 dB plus what you need in order to overcome the link budget, I think. So,
Another aspect of these higher frequencies is it's very useful to play the game of pretend that spectrum is so plentiful and cheap that you don't even meter it as much as you want. What would you do? you wouldn't do any MIMO multiplexing whatsoever. You would give each active user her or his own spectrum in which to work. Second question, how much spectrum would you give each user? Well, you presumably have some power budget, maximum transmit power for each user. You set that, and then you just increase the bandwidth until, guess what? Until the SNR is around 0 dB at the receiver. That's the sweet point, because then you're in the linear part of the logarithmic capacity curve, meaning if I then doubled the bandwidth beyond that, yes, I could cut I wouldn't gain anything at all for the same transmit power. That's the whole point, because my received SNR in each frequency would now be going down by a factor of 2 for each doubling of the bandwidth. And for a long time, I don't think anybody's going to want to do a multiplexing, spatial multiplexing at terahertz, probably not, maybe not even millimeter wave. That's going to be some time to come. So a corollary to that is, if you are an inventor or an engineer or a scientist looking for a breakthrough in wireless or in massive MIMO or something like that, your best chance of marketing this is going to be, guess what, in the mid-band. It's not a millimeter wave, not a terahertz.
So now when we sound a bit negative against millimeter wave technology, I guess it's good to also remember that it has been used for a long time. I mean, for fixed wireless things, I guess nowadays to people's home, but also as backhaul links between base stations, where you have fixed locations, so you can have very directive antennas towards each other. And even if you have predictable mobility, like satellites that are flying over the sky, you know how it's going to move, so you can turn around your transmitter or receiver, I mean, to focus on that one if it's not geostationary. So there it works. But I suppose it is under mobility and like non-line of sight scenarios when you have these real problems. So what is it that really limits us there, you think? Is it the array technology? Is it the propagation physics? Is it the economics? Or will we be able to overcome these issues eventually?
So is your question, Emil, how we can make millimeter wave or terahertz work in mobile environments?
Yeah, can we make that, and what is it we really need to overcome for it to work out?
I don't have the answer to that question. My own research focuses on trying to bring more physics into wireless communication theory in hopes for a breakthrough. And if I achieve such a breakthrough, as I say, it's going to have its best chance for commercial success in the sub-6 bands.
Yeah, it's nice. We are eagerly, I think, all waiting and hoping and working on, finding ways of achieving this breakthrough. So returning to a term and technology that you mentioned earlier today, Tom, holographic MIMO. I'd like to follow up a little bit on that, because you mentioned it, I think, in conjunction with when we spoke about cell-free massive MIMO. What is really holographic MIMO, and how is this supposed to work?
Easiest to think in terms of optical holography, starting in the 1960s after the laser was developed. You had these marvelous three-dimensional pictures. You'd look through it and you could get different perspective as you moved left or right or up or down. And this was done purely with optical means, very clever optics, interference type fringes, that sort of thing. In principle, of course, you could take an optical hologram with an optical phased array. But if you consider, suppose it's a 10 centimeter by 10 centimeter hologram that you want to record, that is, let me see, that's on the order of 10 to the 6 microns by 10 to the 6 microns. And if I want to do sample at a half wavelength and assume a half micron wavelength, then I need 16 times 10 to the 12 optical antennas. And so it couldn't be done. So the idea, of course, of holographic MIMO is that as we go to higher and higher frequencies, could we dispense with discrete transmit antennas and receive antennas, and somehow on transmit control the transmitted electromagnetic field over a rectangular aperture, and on receive record continuously the electromagnetic field. That's the basic idea. So again, there are two aspects to this. One is practicality and the implementation and the economic cost. And I don't know enough about developments in that to say anything interesting. The other question is a more fundamental question. Supposing, in fact, we did record the field or control the field continuously over this aperture, what fundamental advantage does that give us over recording the field or controlling the field at half wavelength intervals with a discrete array?
Yeah, so this is a fascinating prospect, and I feel like this is almost like becoming a potential topic of a podcast on its own. But I guess it might be that I'm not visionary enough, but I've always been thinking that an antenna array would always be constructed from discrete electronics components, and that there would be no benefit of doing anything else than putting antennas that are spaced half a wavelength or further apart. But I suppose this is it's such a novel topic that we don't have all the truths and facts and conclusions yet. And I feel like this is something that maybe we could return to perhaps even at some point. What do you say, Emil?
Yeah, so it is also something that I am very curious about to understand more deeply, because on the one hand, it's like we have the sampling theorem, and we are sort of sampling electromagnetic waves over the air, and then we couldn't sample more than certain half the wavelength or so to gather more information. But then we also have all these breakthroughs when it comes to like super resolution imaging and things like that shows that sometimes we can break those fundamental or supposedly fundamental limits and do something new, and maybe this is an area where that exists as well.
But I mean, a technical question here. I mean, Tom, isn't it? So to my understanding, has been like there is never any benefit of putting antennas closer than half a wavelength apart, right? Because if you have some radiating source, no matter what it looks like or what its directivity is or how it is constructed, and then you enclose it with a sphere, then by taking the sphere and constructing an equivalent source that consists of the sphere but with antennas spaced half a wavelength apart on the surface of that sphere, you can achieve the same external field outside of the sphere as you can with the nominal array or whatever source that you started with. So fundamentally, I mean, when you sample the electromagnetic field at the half a wavelength on a grid with a half a wavelength distance between the points, then you capture all of its characteristics or all of its modes. Is that a correct understanding? And if that's the case, then what would be the point of doing anything else than building an array from discrete components that are spaced half a wavelength apart? And then obviously in practice, I mean, there might be a point of having a sparser spacing simply because you want to cut down on the amount of electronics, but there would never be a point in putting anything more densely together than half a wavelength. Is that something you could comment on? I think we're becoming rather technical here now, but it's such a fundamental question that I think we should try and illuminate it to the extent we can.
Sure, it's a great question. So we like to think, or we often will simplify things by saying the Nyquist sampling rate for an electromagnetic field is a half wavelength. If I get sufficiently far away from a source, that tends to be true. But closer into the source, you have near field, a near field, and things can actually take place faster than half wavelength. So So if one considers, for instance, one of these trends, extremely large aperture arrays, where, for instance, you cover an entire skyscraper with a conformal array, and I'm a pedestrian on the street, anywhere within sight of that building, I'm going to be in the near field. So that's one answer. Another is, Emil mentioned, a super directive antenna arrays. They actually rely, and they've never been, except in an extremely small scale, they've never been realizable, though the concept has been known since 1943. But there you put antennas closer than a half wavelength deliberately to create strong components of the electromagnetic field that very much faster than half wavelength sampling would imply. But again, this is a subject dear to my heart, but which I'm working on, but it's going to require real breakthroughs. The third aspect to consider is, again, consider this, suppose you actually surround the users with antenna arrays. So this could be you're in an auditorium and the ceiling, floor, and walls are covered with conformal arrays. Or again, you're in a canyon of skyscrapers in New York City surrounded by these huge conformal arrays on skyscrapers. You're effectively surrounded by antennas. Then the geometry is totally the opposite of the way we always think of wireless. We think of a base station in the center surrounded by users. This is but if you have this sort of inward pointing geometry, it changes the picture completely. And so I would not want to discount near field effects or evanescent waves.
It might indeed. I mean, of course, here I suppose we'd have to distinguish between being in the near field, in the electrical near field of an antenna element versus being in the geometric near field of an array. But so there's a lot to this, and also super directivity is a topic which I find personally also highly exciting, but which might take us a little, I think, outside the scope of this conversation here today. And perhaps we should do a podcast on electromagnetics at some point. So
we should definitely do that.
Emil?
Yeah, this is something that also I'm working on, so it's something that I would love to talk more about. But I guess we have a few maybe shorter questions for you to see how you are viewing different kinds of popular topic and whether it will make it into the field that you are working within as well. So many people are interested in AI and machine learning kind of things, and they are claiming it will make a huge difference, at least on higher layers where you like have traffic management, user behaviors that are hard to model, so let's use machine learning. Do you see that AI, ML kind of things will have a role to play in the future, or what you're working on, different kinds of MIME or evolutions?
Well, as you know, I work totally in the physical layer. And yes, I agree with you. The higher layers with these very complicated optimization, resource allocation problems, there's every reason to think that AI machine learning could help solve. I know that in optical fiber communication, where nonlinear effects are very strong, there's been some work on actual machine learning for modulation, demodulation. So, the active part of an single mode optical fiber is very, very narrow, and you drive it with enough power, typically by a laser transmitter, that the medium is driven into a nonlinear propagation region. And a lot of clever people have looked at this, but there's really never been any breakthrough on new algorithms, new modulation schemes to either combat or to exploit the nonlinearity. So my feeling always has been that our mathematical tools for nonlinear systems are not all that sharp, and so maybe AI machine learning could help there. But until somebody can somehow build an AI machine, deep learning machine that knows Maxwell's equations or knows Shannon's theorems, I think it's going to be difficult to envision machine learning making great new discoveries at the bottom of the physical layer.
I think a useful way to think about AI and machine learning in this context is that it's like another tool in the toolbox, right? I mean, we have problems where we know the optimal solution and where the optimal solution can be implemented in silicon at almost no power consumption, and there'd be very little motivation or reason to use anything else. There are problems where we have non-Gaussian impairments and highly nonlinear models that are very difficult to identify and so forth. And then we might open the toolbox and pick up the machine learning sledgehammer and throw it at the problem, and sometimes with very good results. I mean, so I think this is really the message also for students that, number one, learn and understand classical model-based signal processing. Number two, also learn the machine learning and AI tools. And I think that's the message that I really like to bring here. So I'd like to return a little bit to applications that will drive future development in wireless and 6G in particular. And we talked a lot about communications, we talked about AR and VR and so forth, but how about sensing? I mean, I had thought for myself that we can already do a lot of things with sensing using like simple Wi-Fi signals, right? I mean, there are, I think, even commercial or gadgets that can sense whether is using Wi-Fi impulse responses, whether someone is moving in a room or even counting how many people are in the room, and check if some, maybe in the home of some elderly people, if they fall and hurt themselves, then they can raise an alarm and so on. And it's like, now supposedly we had not Wi-Fi, but rather massive MIMO. So we have like 100 times more signals on baseband, and we can use these signals for sensing then. That'd be amazing, right? I mean, if you think about the possibilities that the increased spatial resolution would offer us here. So, what is your take on emerging sensing applications, Tom? And maybe this also to some extent connected to IoT and I don't know, telemetry and massive scale sensor networks and so forth. Is something you could comment on?
Sure. Well, for one thing, advocates of terahertz often mention sensing as an auxiliary application in addition to communications. And they point out, of course, that with a physically small array of small extent, you can get high angular resolution. So maybe you can do imaging, look around walls, look through walls, things like that. You can measure Doppler reflection off of human skin and infer breathing rates and heart rates externally, that sort of thing. Okay, that said, you don't necessarily have to go to terahertz or even millimeter wave, though, for interesting sensing. It's simply the fact that with massive MIMO-like techniques, you could get data back simultaneously from a very, very large number of sensors. So many of the things we now do, maybe we could do a lot better if we just multiplied the number of measurements or sensors by a factor of 1,000. I mean, certainly in petroleum exploration, surface seismic exploration, the breakthrough in this, which occurred over the last 30 years, was going from 2D to 3D seismics, such that when you now drill for petroleum, you hit it 50-60% of the time instead of 5 to 10% of the time. It's a matter of just taking data on a much more vast scale. And so could weather forecasting, for instance, this is just an entirely hypothetical question, could it be improved if somehow weather forecasters had continuous measurements of temperature, barometric pressure, and wind velocity every kilometer on a 3D grid over the entire Earth? Could you do better than we're now doing? Who knows? I don't know anything about weather forecasting, but I do know that the only way you could conceivably get this type of data, and you'd want to get it intact. You don't want to pre-prune or pre-process. To get all that data intact to an access point would be some form of massive MIMO.
So I guess one of the development goals of our world is to sort of connect the unconnected in the rural areas of the world, and particularly, I guess, developing countries. So do you think that MIMO technologies can somehow help out with that? Or I guess one thing is just to give it to Elon Musk and his satellite companies, but that will be very expensive solutions. So could MIMO somehow help out?
Sure. I mean, the lower frequency band, say if you work at 100 megahertz, if you put a conformal array on a skyscraper, I'm sure you could go hundreds of kilometers out into the countryside with that, because commercial FM, for instance, I receive a classical music station from New York, which is at around 100 megahertz, 20 miles, which is to say 30, 40 kilometers out in New Jersey. And this is a dumb omnidirectional antenna, so that they're using at the transmitter. So with massive MIMO on a sufficient scale, you could do fixed wireless access to villages for a huge radius around a central point.
Yeah, I guess coverage isn't the issue, but rather whether you get the sufficient capacity with your MIMO array so that over the area that you cover, all of the people in the villages can get the services that they want to have.
Yeah, I would say that the trick is to have a very high capacity link to some central point in the village, and then have a local low power wireless network for local service.
Yeah, it's fascinating. I mean, so massive MIMO might indeed be the technology that closes the digital divide. So I think we're almost about to wrap up here, and sitting on a final topic that I'd like to discuss with you, and that is concerning really how far away we are from the physical limits of wireless communications. I mean, I always argue that performance of a wireless link or a wireless network is ultimately dictated by the physics, right? I mean, path loss is a consequence of essentially wave propagation, or the Maxwell's equations. The same with fading, and coherence is very often a limiting factor. I mean, it certainly would help if the speed of light were 10 times faster, because then we could, enlarge our coherence block 10 times and multiplex 10 times as many terminals, and therefore have utility for 10 times as many service antennas at the base station and so forth. But do we have a good feeling, or do you, Tom, have a good feeling for, like, quantitatively, how far away are we really from the physical limits, from the ultimate, limits imposed by nature of how reliably and how fast we can communicate? Might be the grand question of today. I think it's very open-ended, but if you'd like to give a closing remark on this, I think it'd be very interesting for us and for the listeners to hear.
I think we're very far away from any limits imposed by nature. Even if you don't even talk, even ignoring quantum effects, and so that's why we just have to keep doing research, but we have to be bold. And also, I don't think, for instance, that Shannon theory is going to make any great discoveries in wireless communication, as long as it's a purely mathematical theory, which it is now. And so it has to, communication theorists have to learn more wave propagation physics, for example.
Certainly is something which I think we all three agree very well on. And also, I think a very positive note and a promising statement that there are great opportunities for future research in the field and for further breakthroughs, and that we are indeed rather far from the ultimate limits set by physics and by nature. So with this, I think we are approaching the close-up. So it's been genuinely fun and educational to talk with you, Tom. Thank you very much again for joining us, and Emil, thanks a lot.
Thank you
for co-hosting today. our plan is to continue the Wireless Future podcast with another season running through this semester. And we hope that you'll all log in to YouTube and like and subscribe us there. And also, if there are questions to us, we'll be happy to receive them. You can find our contact information, I think, on the podcast itself and also on our web pages. We're also happy to take suggestions for topics that we could discuss, I think. Emily, you want to add anything here?
No, I think we have covered a number of things in the first season, and now we are having some ideas about what we want to cover in the second season. But we would love to get your comments and suggestions as well. So hope you continue listening.
Absolutely. And with that, thanks again, Tom and Emil, and thank you all listeners. Bye-bye.
Bye.
Bye.